Okay. So today, we're going to be going over with the, so what was the last part we went over? We went over the temperature the other day, correct?
Yes.
Okay. And we did some of the conversions with that? Okay. So now, let's move on to fundamental units and derived units. Okay. Now, fundamental units, if you look at the board of it here, the fundamental units here, fundamental is just another word for basic. It's kind of the building blocks of all the other units. And there are just a handful of fundamental units. Now, one of them, some of these we've already gone over here before. For example, the length is measured in the common unit for that is a meter. The mass is measured in unit grams. Time is measured in seconds. Temperature, technically it's Kelvin, but it also could be in Celsius. One that you're going to be seeing a lot of in this class here is a unit called it's called a mole here, and it's a way to measure the amount of substance. It's a counting unit, is basically what it is. Now, these other two, typically you will not see that in chemistry, it's more in physics. If the intensity of light is measured in a unit called candela, guess what it's based upon? Candles. If you ever bought like a high-powered flashlight, sometimes they'll say like a 1,000,000 candle flashlight. That means the intensity of the light is equivalent to having 1,000,000 candles burning in the same spot. The other one, you may have heard this one here before, when you're measuring electric current, it's measured in a unit called amps or amperes. It has to do with like how many, the charge of the particles as it's going through a wire. But the thing is, these are, like a better term, these are kind of the building blocks of all the other units that we end up using. For example, if you're trying to measure like speed, what's a common unit of how you go about measuring speed? What unit do you normally measure it in? Not miles, that's distance. It's miles, but it's miles per hour. That's a derived unit, okay? In other words, now we're getting into whenever you use two or more of those. So when we're measuring like miles per hour, what you're looking at here is a unit of length versus a unit of time. You're using a combination of these two to come up with a new unit called speed or velocity. If you want to measure the area of an object, normally how do you find the area of an object? Length times width. Length times width is actually a length in two different directions. It's a length of one way and a length in a different direction. Okay, so what we're doing here is whenever you use two or more of these combined together, you're deriving a new unit. Deriving is simply just like another word for you're creating a new unit. So they're built out of these units over here. So all the other units that we use, these are the building blocks of all the other units. And so we're going to be looking at two of these. One of them is the unit of volume. That's a derived unit here. Now normally, if you're finding the volume of a box, how do you find the volume of a box? What's the formula for it? Okay. So volume is measured as a length times a width times height. Is that in your notes? Okay. Now, typically, that is something that you would use if you're dealing with a box. Something a little bit more of a uniform shape to it. Now, if you're measuring it in the unit of meters, let's say a meter times a meter times a meter. So if I'm measuring, the area of my table here, I'll be measuring the length, the width, and the height of it. All I'm doing is measuring a length, and a length in three different directions. Okay? But when I take the unit meter times a meter times a meter, what happens to that unit? It's cubed. So the unit of this is a meter cubed. Individually, these are fundamental units. But by combining three fundamental units, this is now a derived unit. You creating a new unit from those three fundamental units. Does that make sense? Okay. Or, you know, if you're measuring in centimeters, 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 unit would be what? Centimeters cubed. If you're measuring in feet, 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 unit is, okay, cubic feet. If you look at the units, what do you notice about it? What's this a measurement of? This, or this, or this. Those are all units of what? Distance or a length of an object. But then, the one thing that makes it a derived unit here is that they're all cubed. Okay, they're a unit of length that's being cubed. And that's one indication here that you have the unit of volume here, is that it's some unit of length that's always being cubed. All right. Now, there are some units of volume that do not have a cubed unit. Anyone think of any? There are some units of volume where the units are not cubed. Can you think of any? You try and give me a...
No,
Okay.
sphere.
What's that?
A sphere.
A sphere has a cubed unit too. Because if you look at the formula for a sphere, it's 4/3 pi r cubed. So if you have a meters, it's going to be meters cubed here. And there are some units that are measured in volume, but it's not cubed.
Liters, milliliters.
There you go. Liters to milliliters. You don't say liters cubed. You don't say milliliters cubed. It's just liters and milliliters. Or think of when you're cooking. What are some common units of volume? How do you normally, like when you're measuring ingredients, what do you normally measure them in? Tablespoon is one. Teaspoon. Those are units of volume. When you buy milk, normally it comes in what unit of volume? Gallon. Not gallons cubed, it's gallons. That is a unit of volume. Anything else? Cups. Pints, quarts, those type of things here. Those are all units of volume, but the units are not cubed. So there are some units where, you know, if you're typically with more of a solid object, a lot of times it will have a unit of length being cubed. But there are times where you can also have units of volume where the units are not being cubed. One thing I want you to write down here is 1 cubic centimeter is equal to 1 milliliter. Now, one other thing too with the 1 cubic centimeter here is that this is also equal to 1 cc. You guys ever heard cc's before? If you go to the doctor and they'll say, you know, give this person 250 cc stat. Okay, if you ever watched one of those hospital shows, those type of things here, you're getting a shot, they may give you like 3 cc's of medicine. cc stands for cubic centimeter. Okay, that's where the cc comes from here. It's just, rather than saying cubic centimeter, they just say cc. But this right here, 1 cubic centimeter is equal to 1 milliliter. In other words, if you were to take a, say, something which is a container of water, it's 1 cubic centimeter. 1 centimeter by 1 centimeter by 1 centimeter. And this is water. This would be the same thing as if you had 1 milliliter of water. So in other words, this right here, this is 1 milliliter of water down here, but this is also occupying the space of 1 cubic centimeter. In other words, if I were to pour this into a little tiny cube, it'll be a cube that's 1 centimeter by 1 centimeter by 1 centimeter. Okay, that is the definition of a milliliter is also 1 cubic centimeter. Alright. Any questions on that part? So when you're looking at volume, you're looking at basically how much space does an object occupy. And a lot of times we measure either the unit of length being cubed, or sometimes these other units. The ones you're gonna be seeing most often is stuff like liters and milliliters in this class. The common imperial units would be like gallons, cups. Think of it like your cooking type of stuff. Those are units of volume. Any questions on that part? But again, the unit of volume is a derived unit made from units of length in 3 different directions. Now, next one here, density. Does anyone have any idea what density? What is when you're measuring the density of an object? What is that?
Like how heavy it is, kind of.
Wouldn't that be mass? Your hand up?
No.
Here, let me write down the formula for density here.
Mass divided by
Right. Density is equal to mass divided by volume. What does that mean?
So if like 2 things are like the exact same size, one will weigh more.
Okay. So basically, you're looking at how much mass or how much weight or how much material do you have for its size. Okay. One common analogy that sometimes throws people off here: if you have a ton of feathers and a ton of bricks, which one weighs more?
Neither.
What do you mean?
Good thing. It's not
Okay.
huge.
They're both 1 ton. What's going to be a bit different about them, though?
One falls faster than the other.
What's that?
One falls faster than the other.
And actually, not in a vacuum.
Yeah, in a vacuum, because it is.
Mm-hmm.
There's gonna be a lot more feathers.
Okay, so if I would have, I don't know exactly how much I would need here, but to have a ton of bricks, it might be roughly maybe about the size of this table here. For me to have a ton of feathers, rough estimate, I'll probably have to fill up this entire room, maybe a little bit more than that to have a ton of feathers. But even though I have, you know, a ton of bricks and a ton of feathers here, it's how much space do they occupy? Okay, is it possible to make the feathers weigh more than a brick? Yeah, I just need a lot of feathers to be more than the weight of what a brick weighs here. So we're looking at density here, is you're looking at how much mass do you have in a given amount of space, all right? Let me let's go over a couple of examples here. Let me show you an example. I have 2 bottles here. I have a liquid in each one, all right? Now, all I want you to do is I want you to pick up each one of the bottles, just basically lift it up. You can kind of move it around side to side a little bit and then set it down. Don't turn it upside down, don't flip it, don't open it up or anything of that sort, okay? So just lift it up, move it around a little bit, and then pass it down. Pass it down.
Then,
Okay. Now, let's go back over here. How full is that one?
Am I allowed to touch it?
Yeah, you can pick it up and just tell me about how full you
move
think.
it back and forth.
Uh,
Just rough guess here,
like
okay?
halfway?
How full is that, the other one?
Like, down there.
Okay, you're actually pretty close on this one here. You have the amount, has water in it, there's this much water in there, okay? This one, there's this much liquid in it. They both have the same volume. But did it feel that way? I've had some students that they felt it was all the way up here to the top, but they just lift it straight up, put it down, it feels like it's completely filled up, there's only this much liquid in it. So, they both have the same amount of volume. Now, to prove it,
He's down there, the brick in there.
But
He shoved the brick in there.
What kind of liquid is in there?
mercury.
That makes sense.
that's what I.
See it?
That's
Okay.
If this bottle was full, I think, I calculated one time here, I think it should weigh over 30 pounds. If this was completely filled
How
up.
much is mercury?
What do you mean?
buy it.
See it? Okay. Now, the only thing is, they both have the same volume, but they obviously have two very different masses to that. And one common misconception or one misstatement a lot of people make here is that what makes things float or sink here, it has nothing to do with its weight, it has to do with its density. For example, you can have a multi-ton ship floating in the water, but then you can have a little tiny pebble, put that in the water, and it'll sink to the bottom every single time. So it's not the weight that causes something to float or sink here, but the density of it. The ship is actually built so it has a very, very low density. You put it in the water, it's going to be a lot more buoyant. It has a lower density than that of the water overall. A pebble, even though it has a very small mass, for its unit size, it has a much higher density than the ship does. Or same thing here too, if you look at a balloon rising up here. Balloons don't rise because they're lighter than air. Lightness has nothing to do with it. You ever seen during Balloon Fest when they have, those balloons weigh several hundred pounds, but they're able to float here because they have a very low density to them. So now one thing I want to show to you here too, the mercury has such a high density to it in comparison to say something like a piece of iron. If I were to put a block of iron into a pool of mercury, the iron will float like it actually will float better than what wood does in water. And let me show you here real quickly what that looks like. Let's see here.
What did you expect? And you're gonna be blown away by what's next. The Marvel stories continue only on Disney Plus.
Must not.
Nice little breeze today.
Hollywood guys.
Perfect weather for this. It's not too hot. Sun's pretty bright. Hi everyone, welcome back to Cody's Lab. So a little while ago over on the second channel I posted a video of me trying to float an anvil in mercury. Despite it getting lots of views, it didn't actually work. So I wanted to try again. So I got a much smaller anvil. Of course I'm kidding. I got a much bigger tub of mercury. So this ought to get that anvil to float.
Now, I don't think you realize what's going on with this here, just how big of a difference. If you jump into water, and when you are floating in water, if you're staying straight up and down, most of you probably maybe float around your neck, around your head or something like that. Some of you actually might even sink when you jump into the water here. He's technically floating at shin high. So that anvil was actually giving him enough weight so he was touching the bottom of that little tub that he's standing in. When he threw that thing away, he actually started floating a little bit. He's just add a little bit more mercury, he would not be able to touch the bottom. Okay, and it's only shin high. In other words, he's extremely buoyant in this pool of mercury.
Wait,
Wait, he's floating right?
When he's doing this thing here, he's actually just barely on the point where he's almost floating.
This is much easier. Get a little bit more wiggle room. Oh. Also, standing there too long, it cuts the circulation off to your feet.
Okay.
Here.
So when he was talking about right there, because there is so much mass in such a small amount of space, it's actually squeezing his feet down where it's almost like cutting the blood circulation to his foot.
Tingly. There it goes back. Some mercury sloshing in there, so I know they didn't leak. Let's, I got this rag wet. Let's wipe off the top. Get all that oxides and stuff off of there. Oh, isn't that pretty? Since the rag's wet, it sticks right to it. I didn't get all of it, but it's a lot better than it was. Alright, so here's my 110-pound ironworking anvil. I think we got this for making horseshoes and stuff back when we had horses. So let's set it in here and see if it floats. Okay, it doesn't seem to want to stay upright. I'll just let it tip over. There it is. It's floating. Look at that.
That's not hollow either. That's solid. That's a solid block of steel floating in mercury. It's actually floating better than what wood would float in water.
The iron anvil floats because mercury has a density nearly twice that of iron. In fact, due to the density ratios, the iron actually floats better than wood does in water.
Let's push it down.
Notice how much effort it takes to push it down.
Oh, that's great. Here, let's try it again from the other side.
It's about the same effort as pushing a basketball underwater.
Okay, here we go. Push down. Lobs up like a cork. Okay, let's I want to try hitting it with a hammer. I think it dulls the sound quite a bit. Here, let's pull it up out of here. Set it on that. Okay. It definitely sounds a lot different. That's actually pretty nice to have your anvil sitting in mercury while you work it. To deaden that sound. That way it doesn't hurt your ears as much. Pretty good.
Now watch this.
Barely make it wobble by hitting it. Let's just sit that there. Put my hammer in.
Notice what the hammer's doing. Not only is it floating, but look at the wood part of its handle. It's barely able to break through the surface of the mercury.
Would you even use mercury for?
It's used quite a bit in electronics. For example, thermometers is one of them. You can have like the normal, like the old thermometers here, but also in your thermostat. If you have like the old thermostat where you kind of turn the dial, if you take the cover of it off, you'll see a little glass vial inside of it that has a few little drops of mercury inside of it. And what happens when the temperature changes, there's what's called a bimetal. It changes, the two metals change lengths based upon the temperature of it, and it causes little glass tube of mercury either tip one way or the other way. So when it tips one way, the mercury will roll down one side, it'll make a connection, because mercury is also a good conductor of electricity. It'll turn on the switch, and it'll basically turn your furnace on. And then when the house begins to warm up, the thing will tip to the other side, it'll roll down the other side, and it'll flip a switch, and it'll turn your furnace off. As the house begins to cool down, the thing will tip the other way, mercury goes to the other side, turns your furnace back on, and it just teeter-totters back and forth on like that. That's one use for it here. So a lot of your, what they call like tip switches or something like that here, where because of the position of it, that's going to be using that application of it here. Yeah.
How expensive is it?
It used to be fairly inexpensive, but now the problem is they have greatly made it more difficult to get a hold of, because of the danger of it.
How do you think that guy got so much of it?
He's also a chemist.
Um,
And there's also ways that you can actually extract it from, if you have certain types of minerals, you can actually extract it from certain minerals as well. I'm not exactly sure how he got all of that. But then again, sometimes when you have like an old farm, something like that, sometimes they used to have like this type of stuff sitting around. They also use it for a type of like dry cleaning. There's a, I'll talk a little bit about that, how it used to be used for dry cleaning.
So how heavy do you think those like half-gallon jugs were?
Oh, heavy or how much are they?
Like how heavy?
I don't know, I can figure it out here. Give me a few minutes here, I can kind of give a rough estimate.
Why does it roll off objects?
What's that?
Like, why does it bubble on objects? Like, why doesn't it sink?
Has a
down?
very, very high surface tension to it. In other words, it's kind of the same thing that happens with water. You ever see like a drop of water and the way it kind of beads up? It's kind of similar to that, where it's very good at attracting other mercury atoms around it and it pulls it in towards the middle of it. So you kind of get that balling up effect.
Hammer floats too. That's pretty great. Hope you enjoyed. I'll see you next time. Apparently I got mercury in my blood. What good that did.
It's almost like it's like magnetic to like other parts of it.
Mm-hmm. You guys ever seen the Terminator? I think it was Terminator 2, where they had that one character that was like liquid metal. That's how they created that scene. They actually, there's one scene where they broke that Terminator, broke into all pieces, and then he melted and
This
rejoined
is
back
the
together
Checkers
again.
game where grandson and granddad will bond.
And that's how they created that scene there, is they froze the mercury. You had to get really, really cold for it to turn solid. Then he gently heated it up and started melting and start pulling together. But that's how they created that scene here of the mercury beginning to melt. To answer your question here, a gallon's worth of mercury would weigh about 112 pounds.
How did that pick it up with one hand?
It wasn't
That's what I was
full.
thinking. I was like,
It was probably only maybe half, quarter weight full, something like that. All right, so let's do some calculations here. And you'll need your calculators.
oh my gosh, I got one.
So the first one we're going to be looking at here is the top one. What's the density of a material that has a mass of 12 grams and a volume of 1 centimeter by 2 centimeters by 2 centimeters. Okay, so whenever you're working out a problem, once you get in the habit of listing all your given information, so just write down givens. So 12 grams, that's a measurement of what? Mass, okay? So put M or mass is equal to 12 grams. Now, it doesn't give you the volume directly, but instead, it gives you basically the length, the width, and the height. So put down length, width, and height, 1 centimeter by 2 centimeters by 2 centimeters. Now which one is which, it does not matter. Now what we have here are 4 fundamental units. We have a unit of mass, and basically we have a unit of length in 3 different directions. We're going to combine these 4 to create a new unit of density. We're deriving a new unit of density. So now, after your givens, list your formulas that you're going to be using. Okay? So volume is equal to length times width times height.
Mass divided by its volume.
Okay? Density is equal to mass divided by volume. Now, if you look at this, we can do a little substitution in here. Because volume is equal to length times width times height, we can take this part and plug that into here. So therefore, we can say density is equal to mass over length, width, and height. Everyone understand that? Okay, so now, once you have your working equation, you go ahead and start plugging in the values. So density is equal to mass, is 12 grams. Now when you're doing this, don't just put numbers down, put the units in there as well. And then all over 1 centimeter by 2 centimeters by 2 centimeters. 1 times 2 times 2 is what? 4. Now we're keeping the math pretty easy just to, so it's a little bit easier to comprehend what's going on. 4, what?
4 centimeters cubed.
4 centimeters cubed. Now technically that would be the answer, but this is an improper fraction. 12 divided by 4 is
3 grams.
3. So this is 3 grams for every 1 centimeter cubed. Now most often when you write it out though, a lot of times your denominator is going to be a 1, so you just simply say it's 3 grams per cubic centimeter. What does that mean?
Per cube centimeter, it's 3 grams.
Right. So one thing I want you to do too is diagram this. What we have here is, so we have a box that's 2 centimeters by 2 centimeters by 1 centimeter. So 2 centimeters by 2 centimeters by 1 centimeter. So what's the volume of that box? It'd be 4 cubic centimeters. How much would this box weigh?
12 grams.
That'd be 12 grams. So this whole thing here is 12 grams.
That's what I'm looking for.
So when we're saying it's 3 grams per cubic centimeter, what that means is if I were to take this box, I split in half one way, I split in half the other way here, what we're going to be left with is we're going to end up with each one of these segments here, it's going to be 1 centimeter by 1 centimeter by 1 centimeter. This right here is 1 cubic centimeter. Now 1 cubic centimeter will have a mass of how much?
3 grams.
This would be 3 grams, this would be 3 grams, be 3 and 3 grams. So combined, it would have a total mass of 12 grams. So what we're saying here, that this has a density of 3 grams per cubic centimeter, that means for every cubic centimeter of volume, it's going to have a mass of 3 grams. Just like the mercury here has a density, it's about 14 grams per cubic centimeter. In other words, for every 1 cubic centimeter is 14 grams. Water, it's 1 gram per cubic centimeter. Every 1 cubic centimeter of this is 1 gram. So in other words, for its volume, this weighs about 14 times heavier than what this is for its size. Now, is there a way that I can make the water way more than that. Yeah, how?
More of it.
I just have to fill this thing up. But the thing is, for its size, this is has a higher density than this one does. Okay? Now, any questions over this one? Make sense? Okay, so again, this is a derived unit. We derived the unit grams per cubic centimeter, but these were made from these fundamental units of mass and length in 3 different directions. Everyone follow with that? Okay. Let's try the last one here.
Pardon the interruption. I need Rich Gibbons to the office, please. Rich Gibbons.
Okay. Now this next one has to do with a liquid. So it's gonna be a little bit different here. So a solution has a mass of 51.55 grams when 50 milliliters is measured. What is the density?
0.03 grams.
Okay, we'll get to that here in a little bit. So your mass, 51.55 grams. Now this time, the volume is given to you. You don't have to figure that out. This is 50 milliliters. So release your givens.
Milliliters is equal to centimeters cubed.
So the formula is equal to density is equal to mass all over volume. Now later on, you'll get to the point where if I give you the density and mass, what's the volume of it? Eventually we'll get to the part where we have to rearrange this, but right now we're just kind of keeping this simple. Now we don't have to do anything else with this. We already have the mass, we already have the volume. So it's just a matter of just plugging in the numbers. So we have 51.55 grams and 50 milliliters. What is it again?
50 centimeters cubed. Well, 1.031 grams over 1 milliliter
Gram per
per
milliliter. What does that mean?
That's the density?
That's the density of it, but what does that gram per milliliter, what does that mean?
Grams per milliliter.
Okay, hold on guys. That means if I have a graduate cylinder, it's filled up with 50 milliliters. Put it on a scale, this thing here would have a mass of 51.55 grams. Every 1 milliliter would have a mass of 1.031 grams. You do that all the way up to 50 milliliters, you're just adding that up that many times, your final mass would be 51.55. This is one way in which we're able to identify what a substance is based on its density. So you can take a substance here, measure the volume of it, measure how much does it weigh, find out what the density of it is, and look at it basically at a table to find out, identify what that substance is. So for example, if I didn't know what this silvery liquid was, all I have to do is pour some of it out, measure the volume, measure the mass of it, divide those two, and mercury has a very specific density. And from that, I can then look at the chart and find out, okay, this should be mercury then, based upon its density. Any questions on that? Tomorrow, bring your calculators with you. We're going to continue on with some of the calculations.